Hi everyone, my name is Johan. You can find me as at Herland online. I am a developer productivity engineer at Twig. Twig is the open source facing part of the Modus Create software consultancy. At Twig, we use and produce open source software to help our clients solve hard problems. More on that later. So there is an elephant in the scientific community room today, known as the replication crisis. A lot of scientific results are being published, but then other scientists struggle to reproduce the same results. The basics of science itself are based on being able to reproduce experiments. So this is kind of fundamental to science itself. If it cannot be reproduced, then it isn't really science. Data science has a particular responsibility here. Not only is it a huge discipline in its own right, but it has also become a vital component in many other scientific disciplines. And Python, being such an important tool in data science, is of course also affected by this. I'm happy to see that reproducibility in Python and Jupyter Notebooks is already such a popular topic here. Just yesterday, I listened to Nir Barazida talk about how to improve reproducibility in notebooks, and later Eric Levinson talked about how to make ML experiments more reproducible. But let's start here by looking at the status quo. I want to highlight two recently published papers that have looked at reproducibility and Python specifically. First, we have this paper from 4 months ago that looked at reproducibility of Jupyter Notebooks in the life sciences. These researchers collected a large amount of notebooks via papers available on PubMed Central. They then automated a process to copy these notebooks and attempt to reproduce the results. I'm going to jump straight to the numbers they found. Spoiler alert, the numbers are not very good. So here's from their abstract. Out of more than 22,000 Python notebooks, almost 16,000 or 70% declared any dependencies at all. Around 10,000 or 46% had dependencies that could be installed. And around 1,200 or 5.3% could be run without errors. And only 879 or 3.9% could actually reproduce the results in the end. Let's take a closer look at the notebooks that were run, but then failed with an error. This corresponds to the yellow bar, but we want to subtract those that ran without errors. The most commonly raised error by far is module not found error. And in position number 3, we find the more general import error. Both of these are closely related to missing dependencies, and together, these two errors were raised by 29% of the total number of Python notebooks. In other words, if we overlay these numbers and we focus on the failures at each stage, we find that 30% of notebooks fail to declare any dependencies at all. For another 24% of them, the declared dependencies fail to install. And even then, for another 29%, there are errors while trying to import dependencies. So when we look at everything together, more than 80% of notebooks fail to reproduce due to missing or incorrect dependency declarations. Let's move on to the second study. This paper is just a couple of months old and looks at the PyPI ecosystem, a very central part of our Python community. These authors start from the 10,000 most popular libraries on PyPI, narrowing it down to 8,282 libraries that have more than 2 releases. They then attempt to install each and every release of these libraries to find issues in the project configuration. These issues could be related to dependency declarations or other problems that become apparent when you try to install or use a library from PyPI. I'm going to shortcut to the most relevant numbers here. They find that only 65% of PyPI libraries can be successfully installed and imported into your code. Around 5% fail to install for various other reasons, so around 30% can be installed, but may encounter errors as soon as you import them, depending on exactly which parts you import or what your runtime environment looks like. Digging a bit into how they categorize the various failures, we can see that the vast majority of failures are, again, due to missing or incorrect dependency declarations. So both of these papers show that missing or incorrect dependency declarations is a significant and important problem in the Python world. But what do I really mean when I talk about missing or incorrect dependency declarations? Let's quickly recap the basics of dependencies and dependency declarations in Python. This should be familiar to anybody who has worked with Python for a while. So I import some third-party library like NumPy in my Python code. When Python runs this code, it will look in my runtime environment for the NumPy library. This is the dependency. In order for my code to work, NumPy has to be installed. But of course, I have installed NumPy, so this is no longer a problem, right? Well, what happens when you check out my code onto your machine and try to run it? It fails because you haven't installed NumPy. This is the works on my machine problem. The code we run is the same, but the runtime environment is different, and because of those differences, it works on my machine, but not on yours. The real problem here is that I failed to declare my dependency on NumPy. Now, there are many different ways to declare dependencies in the Python ecosystem. I could have written a PyProject TOML or a setup.py to configure my project. Setup.cfg is another alternative, and we could even discuss whether dependencies should be declared loosely or pinned to a specific version. Unfortunately, I cannot go into all of those details in this talk, so instead I'll just go for the simplest declaration here. The bare minimum that any tool would need to be able to discover our dependency and help our users resolve it. This requirements.txt file declares that we expect to have NumPy available when we run this project. It is a declaration of our NumPy dependency. Let's import another module. We add an import of pandas to our code. This is a new dependency, but we haven't yet declared it. Unsurprisingly, we call this an undeclared dependency. We can have the opposite problem as well. Let's say that we experimented with TensorFlow at some point in our code and we did the right thing by declaring it in our requirements.txt. Then later, we ended up not using it after all, but we forgot to remove it from our dependency declaration. We call this an unused dependency. Unused dependencies don't directly affect the reproducibility of our project, and they are therefore not as critical as undeclared dependencies. We still want to avoid them though. TensorFlow, for example, is several hundred megabytes, and this can end up wasting space and time for our users. So to summarize, on the left-hand side, we have our real dependencies, the set of packages that we actually depend on in our Python code. And on the right, we have our declared dependencies, the set of packages that we have listed as required, either in our project configuration or in something like a requirements.txt. We can combine these two sets in a Venn diagram where the dependencies we use but don't declare end up on the left. These are our undeclared dependencies. These make it hard or impossible to use and ultimately reproduce our project. Conversely, the dependencies we declare but don't use end up on the right. These are our unused dependencies, and they add unnecessary bloat to our project. Obviously, we want for all our dependencies to end up in the center. We want to properly declare the dependencies we actually use and only those. Now, at Twig, we help clients across many industries to solve hard problems, and we often encounter projects with or without Python that struggle with reproducibility in one way or another. A little over a year ago, my colleague Noor, who works in the data engineering group at Twig, found herself repeatedly helping projects that suffered from undeclared dependencies. And she wanted to automate the kind of dependency analysis that we just did in the previous slides. Maria, also from our data engineering group, joined her, and a little bit later I also joined. I am not a data engineer. I am part of another Twig group called Scalable Builds. But even if I usually don't work on the same kinds of projects and clients as our data engineers, I still often see the same kinds of issues with respect to lack of reproducibility and the works on my machine problem. Along the way, we had another colleague, Vince, join us for a little while before he had to move on. And finally, Johan joined us as well, almost half a year ago now. Together, we have created FawltyDeps, a tool for finding undeclared and unused dependencies in Python projects. And today, we are 4 co-maintainers that work on FawltyDeps in between our client engagements. The point of FawltyDeps is to do exactly the kind of analysis that we just walked through. When you run FawltyDeps on your project, FawltyDeps will find the set of packages you import in your code and compare it to your declared dependencies. It then produces a report showing you any undeclared or unused dependencies. You can consider FawltyDeps as a linter, not a regular linter for your code, but rather a linter for your dependencies. Here we see FawltyDeps being run without any options in our little toy project. The output first lists the undeclared dependencies that FawltyDeps found, in this case pandas, and below we see the unused dependencies that was found, in this case TensorFlow. If you run FawltyDeps in a large project, you can ask for a more detailed report, and this will also tell you the file and line number where each undeclared or unused dependency was found. Here we see that the pandas import happens in code.py on line 2, and we see that the TensorFlow unused dependency is declared in requirements.txt. So where can you use FawltyDeps? We support Python code both in .py scripts and in Jupyter notebooks. We support any version of Python that is not ancient. And for now, we run on Linux and macOS, but Windows support is already in the works. For dependency declarations, we support the most common formats used in the Python ecosystem today. Setup.py is complicated, as it can contain arbitrarily complex Python statements, but we are able to parse out the declared dependencies in most cases. To use FawltyDeps, you can either install it into your project's developer environment, or you can, for example, use pipex to make it generally available. I also want to emphasize the configurability of FawltyDeps. You can configure everything on the command line, but also via the environment or via a tool.FawltyDeps section in PyProject.toml. Everything is documented in the help option or in the project README. And finally, we also have a nice command line option to quickly create the tool.FawltyDeps section based on the current options. Let's have a look at some more output options. We want to make FawltyDeps as transparent and helpful as possible so that you can understand how and why something ends up in the report. You can run FawltyDeps with list sources to see the files where FawltyDeps are looking for your actual and declared dependencies. This is often the first step in debugging FawltyDeps. Is it actually looking at in the right place? Next, you can run it with list imports to see which imports it finds in your code. And you can run it with list steps to see which dependencies it finds to have been declared. Finally, if you want to write some code to interact with the analysis that FawltyDeps does, you can use the JSON option. This will give you machine-readable output with all the gory details. Now, let's move on to deploying FawltyDeps into your project workflow. Running FawltyDeps on your project once in a while is obviously a good idea, but there is extra value if you can have it run automatically whenever you make changes. The pre-commit tool instruments the pre-commit hook in Git, and it is great for when you need automatic checks to run on every commit in your Git repository. So let's set up FawltyDeps to run as a pre-commit hook. Assuming that we are not already using the pre-commit tool, we need to install that first. The documentation on precommit.com lists a few different ways, but we'll do a simple pip install pre-commit here. Next, we need to tell pre-commit how to run FawltyDeps. We create this precommit config.yaml file, and we add these lines to it. These lines tell precommit where to find FawltyDeps, which version to use, and which parts of FawltyDeps to run. We want to find both undeclared and unused dependencies in the code we're trying to commit here. Don't worry about remembering these lines. You'll find them at the bottom of the FawltyDeps README, either on our GitHub page or PyPI page. Next, we activate the precommit by running precommit install. Precommit is now armed and ready to run on every commit we do. So let's test it out. We add an import panda statement to our code, and then we try to commit it. Precommit fails and prevents us from committing this undeclared dependency. In addition to the failure message from precommit itself, we also get the FawltyDeps output, pointing to which dependency is undeclared and where it was imported. Let's fix this by declaring the pandas dependency properly. So we add pandas to our requirements.txt, and then we retry the commit. And now precommit succeeds, and our commit is done. Finally, let's illustrate precommit catching an unused dependency. So let's add TensorFlow to our requirements.txt, but without actually using TensorFlow anywhere. Now, when we try to commit, precommit fails again, but this time it is the unused check that triggers, and FawltyDeps tells us which dependency is unused and where it was declared. Another way to make sure FawltyDeps runs regularly and quickly catches problems with your dependencies is to run it as a check in your CI system. I will quickly show a GitHub Actions setup for FawltyDeps here. If you use a different CI system, the setup should follow similar steps, but the syntax may be different. So we set up a GitHub action by writing this file into our repository. I'm not going to spend too much time on the syntax here. It should look familiar to anyone who has already set up a GitHub Actions for a Python project. But quickly, we spend a few lines declaring what platform and Python version we're using and getting everything ready. Then we do the usual thing to install the project dependencies. Here we make sure that pip is up to date, and then we install everything from our requirements.txt. And finally comes the FawltyDeps part. We install FawltyDeps with pip, And then we simply run FawltyDeps with the detailed option. If you have configured FawltyDeps in your PyProject TOML, that configuration will of course also be picked up and used by FawltyDeps. Once this is committed to your project, GitHub will automatically run FawltyDeps on new commits and pull requests. So let's see what this looks like when we actually create a pull request that adds an undeclared dependency. Here is a pull request that adds our old friend pandas as an undeclared dependency. Once the GitHub action has run, we get an indication on the pull request overview that the FawltyDeps check is failing. And if we go into the details of the failed check, we can see that the output of FawltyDeps is pointing us to the problematic pandas import. Now, the toy example we've used so far has helped show the basic concepts, but things are always more complex in the real world. Let's draw the rest of the damn owl. First, we will look at a part of the dependency analysis that we've glossed over so far, but that is crucial in order to produce correct results. This is one of the cases where we believe FawltyDeps goes the extra mile, especially compared to doing dependency analysis by hand. And that is how to match import names and package names in Python. It sounds simple. So far, we've imported NumPy in our Python code, and we've declared the NumPy package as our dependency. NumPy happens to use the same name for the package and the import, but Python is not strict about this. The package name you declare as a dependency does not always match the name you need to import in your code. Scikit-learn, for example, is a popular example here. The package that you install or declare as a dependency is called scikit-learn, but the name that you import in your code is sklearn. There are also cases where a single package provides multiple import names, like the setup tools package, for example. It has long provided both the setup tools import name as well as the pkg resources import name. In order to import either of those modules, you need to have setup tools installed. There are even more complex cases as well, which I won't get into here, but it should already be clear that we need some kind of mapping between the import names and the package names. And without a good mapping, we won't be able to correctly match import names to declared dependencies, and we'll end up reporting undeclared and unused dependencies incorrectly. Fortunately, we can usually build a good mapping using your project's Python environment. Now, we don't really know how or where you install your project dependencies. It could be a virtual env somewhere, or you could depend on a system-wide installation or something else. However, let's assume that your project dependencies have been installed somewhere. And when your project is running, Python is able to find those packages and successfully import the modules. As long as FawltyDeps can find this environment where the dependencies are installed, then it can build a correct mapping. So naturally, we put a lot of effort into finding the right Python environments so that the analysis will be as correct as possible. First, FawltyDeps looks for the environments that are associated directly with the project. Without any configuration, we will search under the current directory for any environments located inside your project. Many projects use a virtual env inside the project itself, and these will be found here. You can also pass one or more paths directly to FawltyDeps, and this will limit the search space. This is often useful in a monorepo setting, where your repository can contain a lot of different Python projects. You can also use the pyenv option to directly point FawltyDeps at your project's environment. In addition to looking inside the project, we will also always consider the Python environment in which FawltyDeps itself is installed. Thus, if you install FawltyDeps into the same environment where your project dependencies are installed, you will always get good results. Together, these two approaches give good results as long as the dependencies are installed on your machine. But there might be situations where the dependencies are not installed or not yet installed. How do we deal with these? So first, sort of small aside here, for really advanced users, we have a way to provide a custom mapping where you can tell FawltyDeps directly how packages names and import names correspond. This is usually not used. We don't expect most users to use this, but when it is there, it takes precedence over everything else. Otherwise, we also have an option called install deps. This will set up a temporary virtual env and install the missing dependencies from PyPI, just so that FawltyDeps can get the correct mapping. Obviously, this is quite an expensive option and not always suitable, so it's not enabled by default. And then, when all other things fail, we fall back to something that we call the identity mapping. This is a very simple assumption that package names are synonymous with import names. When we find a package name that we simply cannot resolve any other way, we will match it against an import of the same name. Although this assumption often works out, it is also sometimes incorrect, and that's why we only use it as a final resort. So let's demonstrate how this works in practice with scikit-learn. Remember, we declare a dependency on scikit-learn in requirements.txt, but what we actually import is called sklearn. And the goal here is for FawltyDeps to figure out that these two names are indeed related. Otherwise, it would report sklearn as an undeclared dependency and scikit-learn as an unused dependency. So here's how FawltyDeps figures this out. We take the dependency name scikit-learn and pass it to the first stage of our dependency resolver. This is the custom mapping. As I said on the previous slide, this takes precedence over anything else, but also this mapping is usually not provided, so I'll skip past it for now. Next, we look at Python environments associated with your project. If we can find an environment where scikit-learn is installed, then we will see that sklearn is indeed provided by this package, and our match has been made. Otherwise, we will move on to look at the environment where FawltyDeps is installed. The same procedure here. If it finds scikit-learn, then we're done. Otherwise, we are starting to run out of options. So at this point, if install_deps is enabled, we will create the temporary virtual env and pip install scikit-learn into that. And that will also tell us that scikit-learn and sklearn are associated. And final resort, if install_deps was not enabled, that would be the identity mapping. This would actually do the wrong thing in this case, as it would assume that the scikit-learn package provides the same import names, scikit-learn. Since this doesn't match reality and also doesn't match what's in our code, FawltyDeps would incorrectly report sklearn as undeclared and scikit-learn as unused. As you can see, we try very hard to find the correct mapping before it comes to this. I'll quickly go over some more complexities that we've come across with FawltyDeps so far. This should give you an impression of where FawltyDeps is currently at and where we still have some ways to go. The first one has to do with packages that FawltyDeps would often report as unused, because some dependencies are never actually meant to be imported at all. This goes for tools in your development environment like formatters and linters, or even FawltyDeps itself. It applies to typestubs packages, and sometimes also other packages that are part of some bigger framework, where the actual framework takes care of importing the package for you. FawltyDeps has code to recognize and handle the first two categories, but the last one is still incomplete. So we therefore provide an ignore unused option that allows you to override the unused analysis for a given package. Next, Python is a very dynamic language, and you can often work around missing dependencies or alternatives in the actual code itself, either by conditionally importing a module or by providing an alternative import when the first import fails. FawltyDeps currently considers all imports as if they are unconditional, meaning that we will want all of them to be declared. But as above, when you know better than FawltyDeps, you can use the ignore undeclared option here. Dynamic imports is another thing that is hard to analyze. Sometimes it is actually impossible to know what module will be imported without actually running your code. These cases are currently skipped by FawltyDeps, but we are looking into how we can improve the situation. And finally, there are ways to declare different categories of dependencies in Python. Depending on your context, some of these should be considered optional by FawltyDeps. We have plans to add support for this, but for now, FawltyDeps will treat all declared dependencies as hard dependencies. And with that, let's summarize. Reproducibility matters in science generally, but also Python specifically. A major hurdle to reproducibility in Python is missing or incorrect dependency declarations. FawltyDeps helps you fix this by highlighting undeclared and unused dependencies in your project. FawltyDeps works with Python scripts and Jupyter notebooks across most popular Python versions and platforms. FawltyDeps understands the various ways in which projects declare Python dependencies. FawltyDeps should work out of the box on your project, and if it doesn't, it's easily configurable. And finally, we hope you will make FawltyDeps an automated part of your workflow so that your projects can avoid the works on my machine problem. And that's it from me, really. Thank you for listening, and go check out FawltyDeps. We are on GitHub and PyPI, of course, and we recently started a Discord where we will help you with any questions you might have about FawltyDeps. We also occasionally write on the Twig blog, and there you can also read about all the other things that Twiggers are up to. As I mentioned earlier, we have a data engineering group at Twig ready to help you build and scale your data pipelines or tackle any data engineering problems that you face. My colleague Noor has also started a generative AI group at Twig. We will help you create custom LLM and NLP applications with a focus on private AI, open source large language models, and data-driven evaluation. And with that, I'm happy to take questions either now or you can find me afterwards. I'm at J Herland on GitHub, Mastodon Social, LinkedIn, and elsewhere.